here. It's gonna be a quiet day. Peyton, you found us. Yeah, Holly, I'm okay. I was just brain fog earlier. It was a special day. I took a nap, I'm better now. Both, Christina. Both. It is its own step, and you did do it correctly. So, Andrew, if you remember yesterday morning, I think, I talked about how you can't bend, make that bigger. You can't bend a ring. There's no rotation around that. So if you look at that, it means that the two carbons on a ring are always going to have to be cis to each other. They're always going to have to be on the same side of the double bond, pointing in the same direction. So if you put anything on there, you know, depending on what you put on there, could be E or Z stereochemistry technically, but nobody lists that because there's only one conformation it can take, if that makes sense. So like this one here, across this double bond, the fluorine has the highest priority, and the carbon down here would have the highest priority on that, which would mean that you would have E stereochemistry, right? If you had a CH3 group, though, instead, then now you have Z stereochemistry. So it kind of depends, but either way you wouldn't list it. So if you, for example, take this and, let me do the generate name for structure thing. Notice it doesn't put any stereochemistry on there, because there's no way it could have options, basically. I hope that makes sense. Next question. Cricket, cricket. Oh, who was it that just sent me an email? I think it was, I might be wrong, Candace maybe? Carly? It's one of the, or Kaylee? Somebody with a K that sits in the back corner. I don't remember who sent the email. But they were asking about kind of how not to get confused when you're looking at different structures and trying to determine what kind of stereochemistry you're looking at. And so I mentioned to her that something that's kind of useful is to go through and name something. So let's have a chair conformation here of methyl cyclohexane, right? I'm going to flip the chair, at least attempt to. Okay, so now it's pointing up over there, right? So like, what is the name of this molecule? Shoot, sorry. Trying to make a point and unsuccessfully doing so. All right, so, right, if we look at this, this would just be methyl cyclohexane, right? It's just one is one chair version and one's the other. So that would mean that would have to be considered a conformational isomer, right? Different conformers. It would be the same way if you had butane that's in the antiperiplanar versus like the synperiplanar, right? It's still butane. You'd still name it as butane. So if you're looking at something like that, that makes it a little bit easier. Now, let's say I'm looking at, let's see, 1, 2, 3, up, down. Okay, so now I'm looking at two molecules where it would be 1, 2, 3, 1,3-dimethyl cyclohexane. But if you notice, one of them would be cis and one of them would be trans. And you could work out the R and the S's for these if you wanted to. Onyx, go down. You could work out the R and the S for these, but even if you just look at it and say, you know, one's cis and one's trans, then those automatically would have to be stereoisomers. They'd have to be diastereomers, right? Then let's say, now let's say I'm looking at these two molecules. Now I'm looking at a 1,3-dimethyl and a 1,2-dimethyl. Those have different names. Like the name itself is different because the carbons are in different spots. And so that would mean that those would be constitutional isomers. So, you know, you could have these as enantiomers of each other. You could have them, you know, you could have various, and they could look very similar, but the best way I think to do it is to actually go through and name them, and then kind of think of that table of isomers that I've put on the board about 45 times at this point, I think, and just go through there and kind of think about what it would match up best with. Onyx is going to fall on her butt in a second. Give me just a second. Here, I'll get back in my chair. Go ahead, Onyx. Come. Sorry about that. She came over here to tell me that she wanted up on a chair. Basically, my dogs are spoiled. Ready for more questions? Okay, let's see what we've got. Okay, so Holly, that would just be the regular reaction that we learned the other day, except if you'll notice, there is a potential here because I have a tertiary carbon adjacent to the alkene. That means we can have a 1,2 hydride shift, which is how you would get that product. So I will give a different example, so that way you can still work that one, but that way you'll still kind of see an example of it. Hopefully that works for us. Where's my, there we go. Stylus. So let's say you have, oh wait. Looks beautiful. Give me just a second. I'm going to try and make this look a little better. Honestly, I think my finger does a better job. Okay. Alright. So here's just kind of a basic alkene, and the alkene is next to a carbon that's tertiary. We can add extras on there if we want. So what we could do here is some sort of electrophilic addition reaction, and it could be any of the electrophilic addition reactions that have a carbocation intermediate, and we've seen several of them that do. Both of the ones that are on the exam tomorrow have carbocation intermediates. So just for sake of simplicity, we can do the hydrohalogenation. It requires a couple less steps. So what you can do is your nucleophile will attack the same way we've shown. We still have to break the bond there between the hydrogen and the iodine because hydrogen can't have two bonds to it, right? When we do that, you get a product, or rather an intermediate, that looks like this. Okay, we added a hydrogen on right there, so you can show that if you want. You don't have to show it, it's implied that it's there, but some people like to have it there to keep track. But if you notice, we also have a hydrogen right here, and that is a tertiary carbon. There we go, it's kind of hard to see that. But that means we can have a 1,2 hydride shift. Okay, there will be a driving force to put a carbocation on the tertiary carbon rather than on the secondary carbon. So I'm going to show that. All you do is you take the bond between the hydrogen and the carbon, because it's those electrons in that bond that are moving, and they will move onto that carbocation. Now, I need to make my space a little bigger here. So the product then of the hydride shift would put the positive charge on the tertiary carbon. Okay, and the reaction's not done yet. We still have the iodine floating around that is then going to go on and do the next step. Nucleophile attacks the electrophile. I don't know why I grabbed purple, sorry. So you'd end up with a product that kind of looks like that. Okay, so let me zoom out on that. Make a bigger workspace. Wow, that's bigger than I was hoping. Sorry. Here we go. Okay, so hopefully you can, let me know if that's too small to see. It's kind of small on my screen, but that's because I have all my screens kind of tiny. So hopefully that makes sense. I hope you can kind of look at that one with the cyclopentane, the methylcyclopentene, and figure that one out. Feel free to shoot me your answers on that, anyone who's looking at this, and I can check it for you. And then, okay, Andrew said, could I draw the structure of but2-on3-ol? So that is not a name. There is a situation that happens when you have more than one functional group that would appear as a suffix, okay? And which ones go as a suffix and which one goes as a prefix depends on what's called priority, and it goes by what's the most reactive. Ketones are more reactive than alcohols, meaning they have higher priority, so you would name that as a hydroxybutanone, not a butane 2-one-3-all. We have not gotten there yet, so you can feel free to just ignore it. Okay? I wouldn't give you one like that because we haven't gotten there yet, and we won't this summer. I'll do it in the fall if you have me in the fall, but I won't do it this summer. Then, a constitutional isomer of the molecule that exhibits... Andrew, what are you talking about? Oh, I see what you're doing. Hold on. I was misunderstanding. I thought you were asking me a nomenclature question. You're asking me a drawing question. Hold on. So, butane 2-one-3-all. Butane 2-one. Okay. And so you were wondering... Okay. So a constitutional isomer, right, is one that looks completely different, right? Those were the ones that we did on the very first exam. You look at that and you say, well, there's, right, 4 carbons, 2 oxygens, 1 unit of unsaturation. So how could you come up with a constitutional isomer with that formula? It's 1, 2, 3, 4, so C4, H, 1, 2, 3, 4, 5, 6, 7, 8, O2. If you do the math, it's 1 unit of unsaturation. I know which problem you're talking about. It's 1 unit of unsaturation, but so what have we learned about so far with cis-trans isomers? The only things that we've really seen with cis-trans isomers, you could kind of show it with alkenes, but really you're talking about rings. So let's make some cycloalkanes, right? So 4 carbons, 1 unit of unsaturation, right? There's one that would have cis-trans isomer, right? So that version would be the cis form, but you could also have trans. That's not the only thing you could do, right? Let's do like an epoxide, like what we learned in class today. That's supposed to be CH2, CH3 just looks like a bunch of little lines, sorry. 1, 2, 3, 4, yeah. So that would be some sort of molecule that would have cis-trans isomers that would have that same formula, right? So it wouldn't look anything like that because it would be a constitutional isomer. And Peyton, confusing intermediates and transition states. The intermediate is the reaction. No. So the arrows that you're showing is the mechanism, meaning the physical way that something's happening. Let me put back on ChemSketch. So if you guys notice, there is a thing on D2L that is answering that exact question. So go on there definitely and check it out. But basically, if you have some sort of reaction, right, there's different components. There's the mechanism, and those are the curved arrows that show how a reaction happens. Okay? There's the transition state, and that is, if you're looking at one of those free energy diagrams, it's the peaks on free energy diagrams. Bonds are partially formed. Whoops. There would be partial charges, partial positive and negative charges for a transition state. I talk about how to do that on that thing online as well, so double check that. Every single reaction has a transition state because there's always some sort of bonds being made or broken. An intermediate is I guess we'll call it an unstable molecule between the starting material and the product. Not every reaction has intermediates. These happen in multi-step reactions. So anytime, that's smaller. Okay, so anytime you're kind of looking at a reaction, you could come up with any and all of these, right? Now, not everything has an intermediate. So let me go back to paint here. So if I do something like, let's just do something really simple. Just a really simple acid-base reaction, all right? And I'm giving you an acid-base reaction between a weak acid and a weak base intentionally. Draw it that way. Because this is one that you shouldn't have to think too much to process, right? So it's kind of easier to pick out the parts if you're not having to think about what else is going on. So I can show how this happens, right? We know that the amine, or the ammonia in this case, is the weak base. We know that the carboxylic acid is a weak acid. We know that because we know the carboxylic acid has a pKa of 2 to 4, whereas ammonia is closer up to 30, okay? The weak base is going to be your nucleophile that attacks the hydrogen there and displaces or moves that bond between the hydrogen and oxygen as a lone pair on the oxygen, okay? So we know what that product looks like. We would end up with NH4 plus, all right, and CH3 COO minus, all right? Now this is a one-step reaction, meaning there's no intermediate. But there is a transition state because you'll always have a transition state. And it's essentially what is going on in between. So like kind of think of it as over top of the arrows. So I'm going to kind of scoot this down and show what that would look like. So if you have, and I'm going to kind of redraw this. If you have a nitrogen, oh, that's not going to be easy to show. Instead of a dotted line, I'm going to draw a dashed line because dots are hard to do on this. No. Okay. Imagine that's a dotted line. And then that's going to the hydrogen because that's what that arrow is showing above. The hydrogen and oxygen bond are breaking. And then the rest of the acetic acid is the same. It doesn't do anything. Okay. Now, that would be what the transition state structure would look like. It's got partial bonds. They're kind of halfway in between whatever's going on in that specific step. We show that with brackets. We throw a delta G double dagger up there in the corner, or just the double dagger sign. Okay. You could call this TS for transition state. If there's more than one, you would call it like TS1, TS2, TS3, etc. But now you need to think about the charges. So the way that we do partial charges on transition states is you think about anything that had a charge to start or anything that gets a charge when you're done. So at the beginning, none of our stuff up here has charges. It's all uncharged. The nitrogen in this case is developing a positive charge, and the oxygen's developing a negative charge. So that means the oxygen here needs to have a partial negative charge on it, and the nitrogen needs a partial positive charge on it. Okay, so that's a transition state. Now, an example of a reaction that has a intermediate would basically be not any of them, but a lot of the electrophilic addition reactions, definitely the ones that we learned in chapter 7, because you have a carbocation intermediate. I keep calling it intermediate for a reason. It's the intermediate that's happening between starting materials and products, but it's not a transition state, okay? So if you look at, where's my cursor? If you do one of those free energy diagrams, right, you have your starting material, you have product. It could just be something like that. That would be a one-step reaction. It has one transition state right there where you would put the energy of activation or the delta G double dagger, right? But you could also have one where you have a high energy intermediate, like a carbocation. Oh, that was terrible. So you could have one where you have your starting material, you have your product, and you have some sort of intermediate. Okay. So notice you still have, in this case, you have two transition states. You have two humps in that curve, meaning you have two steps. If you have two steps, you have two transition states, and one intermediate is how that works. Okay. So definitely go and look at the one that I have on D2L. Let me know if it's not opening or something. If you can't see it, that's a whole other set of issue. But I think I'll leave it at that. Let me know if that one's still a question. Are we supposed to know how many intermediates or steps there are? Yeah, because you have the mechanisms. As long as you know the mechanisms, you can answer those questions. And I mean, that's, you know, you learn the mechanism so you don't have to memorize all that other stuff, right? Okay. Hold on, Holly. I don't know what screens I have up right now. Crazy 5 bromo, deck 3 ene. So let's go ahead and put on the parent chain. That's decking 5 bromo. 1, 2, 3, 4, 5. For ethyl. Check my stereochemistry there. So the stereochemistry is wrong. I need to fix that. So the easiest way to do that, right, if I'm looking at that and I'm like, I wrote the wrong stereochemistry. So realize that there's a hydrogen there, right? I need to flip two groups, and the easiest two groups to flip on this structure would be the hydrogen and basically that ethyl group hanging off the end. So I will do that. And there we go. 3Z5 bromo 4 ethyl dec 3-ene. I don't know if you guys just heard Onyx. She's like roughed. She always sounds like she deflates when she does that. No problem. You're welcome, Holly. Hey, Brandon.
Yeah.
I smell something that smells like burning. Did you leave a candle on somewhere? Go look around the house. There's something burning. I don't want to die tonight. I have an exam to give in the morning.
Oh,
Do you smell that?
no.
Brandon was asleep on the couch. I just woke him up because I definitely smell a burning candle somewhere. Either that or we're getting ready to die. Because we're not to die today. I'm only on the 3rd page of writing the exam. Was there something up there burning? What's that smell then? You don't smell anything? Okay. Keep our eyes open for smoke or fire. I'm making faces at my class because they're not asking me any questions right now.
People only have assessment time.
Mm-hmm. I'm just being stupid. I'm touching my tongue to my nose. Because you guys aren't asking me enough questions. I blame you. I think I answered everybody's questions that asked them. If you asked something and I didn't answer it, ask again because it means I didn't see it on the feed. Good Lord. Carly keeps sending me... Carly, are you on the feed right now? Because you keep sending me emails. Yes. That is correct. Oh, there's not one, Andrew. Sorry. Thought I counted out 10. Whoops. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, sorry. There you go. Now there's 10. Can I give an example of some of the new functional groups we learned for the exam? Okay. I'd have to look at my list of all the things I made you learn for this exam, because I don't remember which functional groups, but like... Here. There's one. There's one. Bird out there? There's a really loud bird outside. All right, Peyton, there's 2 molecules with 4 functional groups. Go! Almost done with this tray of blueberries. I bought a tray of blueberries and I've eaten them all in 2 days. So, hopefully you see the SH and you go, that's a thiol! And if you have an oxygen between 2 carbons like that, that is an ether. And then down here, where it looks like a carboxylic acid, but it has a carbon group attached to the oxygen. Yep, that's an ester. That's right. What about this one over here? That one's a little harder. So you have a carbon, double bound to an oxygen. That's attached to a nitrogen. What is that functional group? So far, we've only ever seen them with hydrogens attached to the nitrogen, but they all count as the same functional group. Ends with an A. That's my girl. You can hide. Nice work. Still have time for a few more questions if you guys have any. Oh, that one's tart. You need to classify when there's a 1,2 hydride shift. That's definitely not the worst typo I've seen for shift before. So I don't know what you mean by do I need to classify it? Like if it's something you're trying to show with the mechanism, you need to show that as part of the mechanism, that one arrow that shows the hydride moving over a carbon. If you're just trying to show a reaction, then you don't need to do that. I mean, you would show the product with the shift in, as part of the product, but you wouldn't have to do it. To like write down plus hide red shift. Announce it present in the mechanism. I mean, if you just show it as part of the mechanism, that's fine. It would just have its own, and that would have its own intermediate, and it would have, right, transition states for that component as well. There's a good section in your book on chapter 6. I don't have that on me. It's upstairs under my bed. Yes, I sleep on top of my organic chemistry textbook. The book has some energy diagrams where it shows lots and lots and lots of basically humps in the reaction, and so each of those would be, you know, a transition state, intermediate, transition state, intermediate. You can have quite a few of them per reaction. And some of them just have one transition state and no intermediate, but you could have some that have lots and lots. Ones in biochemistry tend to have a whole lot. Well, Peyton, you said you're barely getting internet service right now. I'm not surprised that there might be some issues there. I'm just happy you were able to come here tonight with us. We all know you live in the middle of nowhere. Well, if anybody didn't know, guys, Peyton lives in the middle of nowhere. Alright, we're starting to get to radio silence, people. I'm going ahead and hopping off because I got to finish writing the exam anyway, and then I got to proofread it. I'll still be up for a few hours, obviously, so if you have any more questions, you can email them to me. I think I've emailed everyone that has emailed me so far. Sorry if there was a couple hour delay. I came home and took a nap, so I would feel better. Yeah, I think that's it. Exam's 4 pages like normal. I have a page of nomenclature, a page of extra material just from chapter 5, a page from chapter 6, and a page from chapter 7. So, I think that's about everything. So, anyway. Well, yeah, you guys have a good night. You too, Peyton. Thank you. You're welcome. Have a good night. 7 a.m. I will keep taking emails tonight, but keep up the good work, guys. We're almost done. We have like a week and 2 days left or something. I mean, it's not even that. What do we have? Tomorrow's Wednesday, Thursday, Monday, Tuesday, and Thursday. We have 5 class days left, so we're almost done. Hang in there. We're almost there. I'll see you all in the morning.